Okay, so it looks like I've kind of lost the first part of the video that goes with this, so I'm re-recording this. So we're talking about dissolving ionic compounds, and what we've done so far when we've discussed mixtures, we've focused on substances that are in non-chemical combination with water, okay? In other words, the substance that's in the water is simply mixed with the water molecules. It's not bound to it. So an important part of chemistry is that we often want to be able to separate mixtures from each other, and we can usually do this based on the physical properties of the substance in the mixture. And if the mixtures are heterogeneous and involve substances that don't mix well and have significantly different densities, and this is a type of suspension. Remember again, we have two types of heterogeneous mixtures. Suspensions are ones where you can actually see the fact that something is a mixture of things. Stuff is suspended in something else. We should simply be able to separate the two because one will actually float on top of the other one, like you can see in this picture here. Okay, you can see the oil floating on top of the water here. So if the mixtures are heterogeneous and involve particles that will settle out or are dispersed but still large enough to be visible, and this is another type of suspension, we should be able to filter the particulate material. And here's an example of doing that. We've got a funnel here, and we've got a filter in the funnel, and we're going to do something called gravity filtration. We're going to create a vacuum inside the flask here, inside the Erlenmeyer flask, and that's going to pull the filtrate or the part of the solution through the filter, and will allow us to collect the stuff that's suspended in there. If the mixtures involve particles that are too small to filter and are well dispersed but still exhibit the Tyndall effect, and you'll see a description of this down here. These are mixtures that we call colloids, right? That's the other type of heterogeneous mixture. We may still be able to separate the material with activated charcoal and filter the charcoal with the adsorbed material out of the water. And so just to show you what the Tyndall effect is here, if microscopic particles are present in mixture with water, which is a colloid, the water may have a uniform appearance, okay? So without the light shining on it, the water has a uniform appearance. However, shining a light beam through the mixture will reveal the presence of microscopic particles. Light's going to bounce off them, and you'll actually see the beam of light as it's passing through the liquid. And that will not be present if no particles are present in the mixture. And over here on the left side, you can see a pure substance or maybe a solution, but it's not a colloid. And we call this effect where we get this light bouncing off of the particles that we can't really see, the Tyndall effect. And this is useful for determining if the liquid is a colloid. We've also started to discuss another type of mixture in which particles are so small they're uniformly dispersed, individual molecules or ions, and recall that these are homogeneous mixtures that we call solutions. So we've said that the compounds that dissolve in water could either be ionic or covalent. Both of these types of things can solve in water. In ionically bonded substances, the bond forms between positive and negative ions. And we know this is just a review, right? When And remember, electrons are transferred from the valence shell of one atom to the valence shell of the other atom. This is what forms that bond, right? On the other hand, in covalently bonded substances, the bond forms when electrons are shared. Remember, the term covalent means sharing of valence electrons. Water will dissolve a lot of ionic compounds, or many ionic compounds, but only some covalent compounds. And the reason for this lies in the nature of the chemical bond itself. We recently introduced the idea that if a compound does dissolve water, only so much of it will dissolve in a certain amount of water. Only a certain amount of it will dissolve in water at a given temperature. And we called this amount the solubility of the compound. And we defined it as the number of grams of the compound per grams of per 100 grams. Let me erase that there. Per 100 grams of water. We also discussed the dependency of solubility on temperature. And we said that we could create a graph. We could graph the solubility of any substance compared to the temperature to create a solubility curve. But what's going on at the atomic and molecular level, and what governs how much of something will dissolve? That's something that we want to know. One thing that we've mentioned briefly, but we'll go now into further detail, is the polarity of the water. We've previously said that the water molecule, while totally neutral, because it has the same number of protons and electrons within the molecule, it has an unequal distribution of charge. And this gives the molecule a polarity similar to the polarity of a battery. So one has a positive end or a negative end, and this polarity affects whether or not substances will dissolve in it. And this is kind of how I view this. This isn't like an official diagram or anything like that, but this is how I view the idea of this unequal charge distribution. Remember, we've got 6 electrons for the oxygen atom, and then each hydrogen atom adds an additional electron. And we have the outer shell of the oxygen here, and that's got these 8 electrons in it because it's sharing 2 electrons with hydrogens. And then hydrogen has its outer shell, its only shell, filled as well. It's got its 2 electrons, but notice how close we've placed the electrons to the oxygen. The shared electrons here between the hydrogen and the oxygen are close to the oxygen, and that makes this end of the molecule more negative, and it makes this end of the molecule more positive. So that's our diagram that shows that polarity. Polar molecule is any molecule where there's an unequal distribution of charge, such that the molecule has one or more partially positive portions and one or more partially negative portions. So, as with the chemical properties of any compound, this property comes about because of the structure of the chemical bonds that hold the oxygen and hydrogen atoms together. Okay? So, knowing that the water has this polarity, how do you think the water molecules will arrange themselves related to each other? And we've shown this diagram before as well. If I have a water molecule here in the center, and I say that that end's negative and this end is positive, a force of attraction to neighboring water molecules is going to develop. So if I've got a neighboring water molecule over here, the positive end is going to attract to this negative end here. And then the negative part here is going to attract to this positive part of a neighboring water molecule. And then the positive end here is going to attract to this neighboring water molecule. And then the positive end of this water molecule is going to attract to the negative end of this water molecule. Okay, and so water molecules in a sample of water will arrange themselves sort of like this. Now, it won't stay exactly like this. These forces here, and remember these are interparticle forces. These interparticle forces are not strong enough to keep them completely locked into place unless the temperature is low enough, in which case we have ice, right? But in liquid water, these particles will constantly be shifting around and making and breaking these bonds as the particles move. But in general, this is how water molecules will arrange themselves related to each other. Okay, and it's at this point where the next recording, the next video picks up. So I'm going to stop this video, and then you'll need to go look at the next video to finish out the rest of this set of notes. Okay?